Okay, here we go with the notes for 3F for the Math 4 course. We're going to be looking at log functions and exponential functions when it comes to a table with x and y values. We're also going to try and use regression models to solve real-world problems. We're also going to take a look at some other things involved in these regression models, like residual plots. We're going to actually spend a few minutes looking at that, on how that can have an effect on your decision. Now, first example, we're supposed to take this table and we're supposed to plug it into Desmos in two different ways. The first way is where A is the x value and B is the y value. And then they want us to try it backwards, where B is the x value and A is the y value. And we're going to look at both exponential and logarithmic equations on both. And then, because it said find the regression line for each. And so we're going to do a total of 4 equations out of this. Anyway, so here is the first one, where the 1 through 9 are the x's. Now the exponential here, oops, I guess it would help if I would turn my pen on. All right, exponential. Really we're saying 1 times 1.5 to the x. We really don't need the 1. The rate we're rounding this, and we're supposed to round it to the nearest hundredths, I believe. So you might as well call it 1.5 to the x. And look at that r squared value. Look at that r squared value. It's 1. It is exactly 1. This is dead on for an exponential. Now, if I try and look at it as a logarithm, well, for starters, my r value is 0.6. So it's not that good. But I will go ahead and write the logarithmic version of this would be negative 6.81 plus 31.24 log of x. Oops. All right, and I wanted to go ahead and notice with this graph, these dots are dead on with the exponential curve, and the best fit curve of the logarithmic just is not close at all. Now this, when we go to switch places with x and y, this is what happens, is that suddenly we discover that all of our dots are dead on for the logarithmic curve. And when I look at my exponential, it's not exactly close, not as close as the exponential is, not as close as the logarithm is. Let's look at what some of the charts are saying over here. My exponential has an r squared value of 0.7, but my logarithm, not surprising, has a value of 1. Now, what this does is this establishes for us that logarithms and exponentials are indeed inverses of each other. Because when I switched my x and y, and first it's an exponential, perfectly fit curve, and then I switched them, and now it's a perfectly fit logarithmic curve. These are inverses of each other. All right, so we're going to write out, let me do this. And we're going to write out what we've got here for my exponential. Which would be y equals 3.3 times 1.03 to the x, and my log, scrolling down a bit, would be really 0.0006. You might as well call it 0 plus 5.68. Well, I don't need the 0. 5.68 log of x. Okay. All right. And that should take care of that. Now, what we need to do is we need to go down over here and graph these. First, where A is x and y is b, and then when we reverse it, and we're going to see something interesting happening with these two curves. Now, I'm going to go back here because I think it would be easier to graph this. Whoops. I need to move this guy over a little bit. All right, so I can look at my chart and be graphing x is 1, y is 1.5, x is 2, y is 2.25, x is 3, y is 3.38, x is 4, y is 5 and something, x is 5, y is 7.5, x is 6, y is 11.39, something like there. Next one's 17.09, 25 point something, and 38 point something. And so I can see my curve here going around up like that. That is a classic exponential curve. But then again, our exponential curve had an r-squared value of 1, which means it's dead on. Now we're going to switch over to the other side where my logarithm had an r value of 1, and we're going to see what happens when we graph this other side. Now that's going to be 1.5 on 1, and 225 on 2, and 338 on 3, and 5.06 on 4, and 7.5 on 5, and 11.39 on 6, and 17 on 7, and 25 on 8, and 38 on 9. 38 is going to be over here. And so we're doing something fairly similar. So we get the idea that if we had drawn them on the same scale, on the same graph, they would have appeared to be reflections of each other across y equals x. All right, so we've sketched, we've found the regression lines for each. That was not meant to be there. All right, let's move on to the next one. We have a table of wind speeds at x and wind chill factors at y. So the speed is x and the temperature is y. And when we plug those in, we get something that resembles this. You know, those green dots are all of the players in this. And so they ask us to find the equation for each one, give the r squared value for each one, linear and quadratic. Blue is the linear, green is the quadratic, black is the exponential, and red is the logarithmic. And so we're going to take a look at the numbers here and see what we're coming up with. All right, so those are the numbers there. So I'm going to scoot this over a little bit. That's not what I wanted. And then I'm going to do this. All right, so first was the linear. Linear was this guy here. I can look at my parameters down here and find what I need to write the equation. Y equals negative 1.09x plus 9.31. That's rounding to the nearest hundredth. That's 2 decimal places. And I'm just going to go ahead and go with r squared on all of these just to be consistent. R squared for this one is 0.9004, which is really good. But let's see what the other guys do. Quadratic is down here. Quadratic. All right, quadratic, we're going to do that. And then we're going to have 0.09x squared minus 2.37x, and then 12.17. Come on. There it is. 12.17. And then our r squared value is 0.9912. Now that's even better. That's even better. Now, next is going to come the exponential, which will be this guy in black. All right, so we're going to say y equals, and for exponential, it's going to be 16.52. And then we're going to multiply this guy on the inside of the parenthesis raised to the x. My r squared value is 0.8886, which is good, but not as good as the 0.99. And then the last one is the logarithm, which is the guy in red. Well, that's right, we didn't do our, yes we did, okay. All right, logarithm, y equals 10.68 plus, or I guess I should say minus, minus 12.25 log x. My r squared value is 0.9873. Now, just by looking at my values alone, my r squared values alone, it looks like the parabola is the best bet. It has 0.99. The logarithm is not far behind it at 0.987. So we're going to bear this in mind. I want to show you something really, really cool about the R squared value. Because when you, I guess I'm going to have to do this over here. Each of these, you'll notice, well, except for the linear, and except, why does the exponential not have residuals? That's interesting. But the log does. That's weird. Why does it not have? Maybe if I plot them. Oh, because I've already got them up there. I did them earlier. Okay. All right. Each equation, when I zoom in, let's take the green guy, for instance. We talked about how residuals are the distance between the dot vertically and the best fit line. You know, so that distance would be about 2 notches there, whatever they're worth. They're worth about 1/10 roughly. And as I go down here, further down the line, I look at how far is this green dot from the green line? How far is it from the green line? Now, instead of plotting them against a curve like that, what if we took those distances and put them all on the x-axis instead of having them being distance from the curve? Let's see now, that would be the green one. Wait a minute now. All right, the parabola is E4. All right, so this would be, the black dots would be how far the green dots are above and below the green line. As a matter of fact, I can also take out some of the rest of these just so that we can focus on the parabola just for, you know, that was the one that had the best R squared value. And this is part of the reason why when I look at the residuals and I replot them, how far above and below the line they are, these black dots represent how far above and below the green line they represent. And it's kind of a random scatter here. There's some up, some down, not really a pattern to it. Now I want you to watch what happens when I start looking at, say, for instance, the exponential curve. And let's see, that is E1. So when I start looking at the residuals and I'm plotting the distance, how far the green dots are from the black line. And I'm noticing that, you know, yes, there's some up and some down, but they're actually forming a bit of a pattern. There's almost a bit of a parabola happening there. Anytime there's a pattern like that, there's probably something better out there than what you've chosen. All right, that is one way of looking at it. Let's do the logarithm. The logarithm was E2, and that is that guy. And so when I look at the blue dots, they are fairly well scattered above and below. There's not really a pattern of, you know, a curve or anything like that. So I can feel fairly confident about the logarithm that it is also a really good fit. Now, let's back up and ask the ultimate question. I'm going to put all 4 of them back on here. And I will ask the question, when it comes to wind chill factor, you've got the blue straight line, you've got the red logarithm curve. It's actually a negative logarithm because it's flipped upside down. You've got the green parabola, you've got the black exponential. And the reason why the exponential is not curving the other way is because the base of the exponent is a fraction less than 1. That causes it to kind of flip around the other way. So which one of these actually reasonably patterns what temperatures should do as wind speeds increase? Now look at what's happening with the parabola that's actually going back up. That's not what you would expect of wind chill. If my wind chill factor drops down here and then I start having faster winds, it's going to warm up. That's not going to happen. Now, it's not going to plunge straight down on a straight blue line. And the problem I have with the exponential is that it kind of bottoms out at 0, and we've already got several values that are below 0. So I don't think the black line is useful either. About the only one left that's following a reasonable pattern is red, which is the exponential, the logarithm. The logarithm. So when we go back to this page, and we look at the individual plots for regression, let's do that. Oh, that was that. Let's do that. And let's see if we can somehow bring this. Oh, I know what I can do. I can do that. All right, and we can zoom in a bit. And so now we need to answer the question, which one of these does best? When I look at the blue straight line, I would almost describe it as not helpful. When I look at the quadratic, which is the green, it's going in a bad direction. I don't need for my temperatures to suddenly go up the faster the wind speed gets. That's not how this works. When I look at my exponential, it bottoms out at 0. But the logarithm seems to be the best fit of the 4 of them. Now, I would remind you of our r² values, that even though quadratic was best, logarithm was right behind it, 99 versus 98.7. So the logarithm was not too far behind it. So when we want to project the best wind chill factor for wind speed of 29, that's where we're going to go back to our graph. And this time we're going to follow the logarithm until it reaches x is 29, which is going to be right about there. Now, I'm going to have to zoom in a bit to get it more precise. There's 29. Oh. There's 29 itself at negative 7.24. When the wind speed is 29 miles per hour, the wind chill factor is negative 7.24. All right, so we're going to go back over here, and we're going to say negative 7.24, and that is degrees Fahrenheit, and that is from the log curve. And that is our best projection for this because we've kind of ruled out the other 3 that there was problems with them. Now that we've gone through this process, we're going to go through it a second time with this set. And I've already got things plugged in so that we don't have to waste time while I'm typing stuff in. But this is a case of the more hours that you study, the higher the test score. Now this is a group of students that scored 50s on a pretest. And so they've taken a pretest and they all scored the same thing, but they turned around and studied how many hours and how did they do on the test score. So this is where we're going to plot them and begin to make reasonable assumptions. I think the very end of the thing says, so how long do you have to study to get a 91? All right, so we're going to start here with the equations for each regression and also list their r² value. And so this is going to, I'm going to move that over there. And this is going to come over here. And this is the data set. And so I'm going to start with linear. Linear in this case is black. And so we're going to say y equals 1.96x plus 61.69. And then we're going to come over here and say that the r squared value was 0.8569, which is not bad. All right, and then we're going to, next is the quadratic, which is red. And so that is going to be, according to this, and I'm going to go ahead and let you see what these points are gathering like, and you can see the curves already. And we'll talk about this in a minute. Let's get our numbers written down first. That's going to be 0.20, negative 0.20x squared plus 3.91x plus 58.50. And yes, if you're doing this to two decimal places, the nearest thousandth, that's going to be 3 decimal places. All right. And we're going to have to go back and do linear again, too. Nearest thousandth is 3 decimal places. I thought I had rewritten that as 2, but oh well. Well, we're already in the mood to do quadratic here, so let's do negative 0.195 x squared plus 3.91x plus, no, that's 3194 x plus 58.503. All right, and then our r squared value is 0.8937, which is a little better than the linear. Linear is going to be 1.962x plus 61.692. All right, we're good there. Now let's see, the exponential was blue. All right, the exponential was blue, and so we're going to start off this way, and 62.236, and then in the parentheses 1.028 to the x. And our r squared value there is 0.8464. So of the 3 so far, this actually has the worst best fit numbers. And then lastly, it'll be in green. And we'll write y equals the first one, 052 plus 17.715 log x. And our r squared value is going to turn out to be 0.9379. So it actually sounds like our log is the best fit. Now, let's look at the relationships here. I'm going to go ahead and expand that out a bit. we can see what's going on here with the dots. None of them are really, really close to any one of them. And in fact, just in looking at the grander scope of things, we're talking about the number of hours you study on X and the way your score goes. Now, honestly, I don't see blue or black being a viable option. I really don't see your scores going up like that. The more hours you study, suddenly your score rising like that. I don't think that's the case, and I don't think the black line is the case. The green is very good. The red is probably not a good fit as well, because you don't expect your scores. I know there's the law of diminishing returns, but this is kind of ridiculous. They're basically saying that once you get past 10 hours, you start losing points. I don't think it quite works that way. So I'm going to go with the green line, which in this case turns out to be the logarithm. And so that's going to be our best fit. So we're going to go back and say about the other guys that the blue and the black, the linear and the exponential were not a good fit. The quadratic went in the wrong direction. We really don't see anybody spending more than 10 hours suddenly losing points. So our logarithm seems to be the best fit. So they say, so how many hours would a student have to study to get a 91? So we'll go back here, and we're going to focus on this one now. If he wants to get a 91, wow, 91 is up here. And I think we're going to have a problem landing right on 91. Yeah, we have to zoom in a bit. 91 exact, well, 91.01. We'll go in a little bit more. 91, there's 91 exact. And it would take about 49 hours to get a 91. Wow, that's ugly. Of course, this was a group that got 50s on the pretest, so maybe that is justified. But according to this curve, it would take them 49 hours to study to get a 91. So that's what we'll put here. 49 hours by the log curve. All right, and I think that does it for that set of notes.